When you flip a light switch, what do you actually picture happening? You probably imagine electricity as, a substance, something flowing through a wire like water through a hose. But what if I told you that entire idea is just fundamentally wrong? Today, we're going to peel back the curtain on the unseen world of electricity. And trust me, what we find is going to change how you see pretty much everything.
So let's start with a really simple question. We all know light is fast, right? But what about the electricity inside a plain old copper wire? How fast do the actual electrons, the tiny particles of charge, really move to power your stuff? What's your gut tell you?
The answer is pretty shocking. The individual electrons are actually drifting along at an incredibly slow pace, usually less than a single millimeter per second. I mean, that is a truly glacial speed. And right there, that creates a huge, huge paradox.
Yeah, think about it. If the electrons themselves are barely crawling along, how in the world can a lamp all the way across the room light up the very instant you hit the switch? It feels immediate. And that is the central mystery we're going to unravel today. To really blow this mystery wide open, we need a thought experiment. It's a puzzle that's so absurd on the surface, it perfectly exposes the lie that, well, we've all been told about how electricity actually works. Okay, so picture this. You've got a switch and a light bulb sitting just a meter apart from each other. Simple enough. But here's the twist. The wires connecting them are insanely long. Imagine each one runs 300,000 kilometers out into space and then comes all the way back. That's roughly the distance to the moon. So when you flip that switch, how long does it take for the bulb to light up? Most people's intuition screams 1 second, right? I mean, something has to travel the full length of that incredibly long wire. But the real answer is absolutely staggering. It takes about 3 nanoseconds. That's just the time it takes for light to cross the 1 meter of empty space between the switch and the bulb. It lights up almost instantly. But how is that even possible? And right here, this is the secret. This is the crucial point. The energy isn't a package being carried by electrons inside the wire. The energy travels as an electromagnetic wave in the space surrounding the wires. The wires, they just act as guide rails for that wave. So, okay, if the energy is moving through the empty space around the wires, how do we even track it? Well, it turns out there's actually a map for this invisible energy highway. This map is called the pointing vector. Now, don't worry about the math or the fancy name. Just get the core idea. Wherever you have both an electric field and a magnetic field at the same time, energy is flowing. And this pointing vector, it points you in the exact direction that energy is headed. It's like a cosmic compass for energy flow. So let's just put it side by side to make it crystal clear. The old model, the one we all kind of grew up with, pictures electrons as these little delivery trucks, carrying energy all the way from the power plant. But our new model shows us the truth. The power plant sets up this huge electromagnetic field, and that field is what carries the energy through space, with the wires just shaping and guiding its path. Now, this whole fields not flow idea isn't just a weird thought experiment. It's the real-world principle behind some seriously advanced technology you might even have right there in your kitchen. If you've ever seen an induction cooktop, you've witnessed this field concept in real life. It's kind of magic, right? You can put a paper towel between the pot and the cooktop, boil water right on top of it, and the paper won't even get brown. If electricity was just about heat flowing through a conductor, that would be totally impossible. So, what's the deal? It's the field that's doing all the heavy lifting. The cooktop generates a rapidly changing magnetic field. That field passes right through the glass surface like it's not even there and creates a swirling electrical current, called an eddy current, directly inside the metal base of the pan. So the pan itself becomes the heating element, fighting against this current and generating its own heat. The energy literally traveled through the air, not the cooktop. Okay, so now let's use this new way of thinking to solve a mystery that has puzzled scientists for millennia. Seriously, it's something you've probably experienced every single time you've touched a doorknob in the winter. Yeah, let's talk about static electricity. The ancient Greeks wrote about this stuff way back in 600 BCE. And for over 2,500 years, we didn't have a complete explanation for something as simple as rubbing two things together to create a spark. I mean, that's an incredibly long time for such a common thing to stay a mystery. But now we finally have the answer. It turns out it's all about these tiny nanoscale bumps that exist on every single surface. When you rub two materials together, these microscopic imperfections, they bend and they deform. Think of it like bending a little piece of plastic back and forth.
That physical strain, what scientists call elastic shear, actually generates a tiny voltage. Billions of these tiny bent bumps, each one creating a tiny voltage, add up to the big static charge that gives you a shock. It's a physical action creating an electrical field.
Let's check out one final example. And this is one you can actually hear all around you. The next time you walk past one of those big, gray utility boxes on the street, just stop for a second and listen for that distinct hum. That sound is physical, audible evidence of these invisible fields at work. That sound is caused by a phenomenon called magnetostriction. Inside that transformer box, incredibly powerful magnetic fields are being created. These fields are so strong, they physically cause the metal core inside, which is made of something ferromagnetic like iron, to expand and contract. You are literally hearing the metal change its shape in response to an invisible force. And we're not talking about a slow vibration here. We are talking about the core physically changing shape 120 times every single second. It's a tiny, super fast movement, way too fast to see, but more than enough to create that constant, powerful hum. And you know, while that steady hum is perfectly normal, different sounds can mean big trouble. A sharp crack or pop can indicate dangerous electrical arcing inside. A gurgling sound could mean there are problems with the cooling system. And loud banging? Well, that could mean a serious mechanical failure is about to happen. The sounds are a direct diagnosis of the fields inside. So what does this all really mean? When you put it all together, from a tiny static shock to an induction cooktop to the hum of the entire power grid, all these things are pointing to the exact same conclusion. We are completely surrounded by an invisible, powerful, and absolutely essential world of fields. This quote really just nails it. A power plant does not ship fresh electrons. It nudges charges already in place, setting up changing fields. The power company isn't shipping you a substance. They're orchestrating a dance, creating these perfectly organized fields that carry energy at nearly the speed of light. And it's such a powerful reminder that the most profound principles of physics aren't locked away in some distant lab. They are right here, right now, powering the most ordinary parts of our day, from the toaster that makes your breakfast to the phone you're probably holding in your hand. So the next time you see power lines overhead, don't just picture them as pipes full of electricity. See them for what they really are. Guardrails for invisible waves of energy flowing through the space between them. We live inside a huge network of these energy highways. Now that you can see the unseen, what will you notice next?